Okay, so we're going to continue today picking up right where we left off in the previous lecture. So we're going to discuss in more detail this algorithm which allows you to find the shortest path through a weighted graph, where the way you measure distance is in terms of the weights on the graph. Before we continue, I just wanted to point out a correction from the last lecture, which I also emailed everyone about. So in this example, when we were discussing Hamiltonian paths and circuits, I had originally claimed that this graph does not have a Hamiltonian path. Of course, that's not true, because you can pretty easily find a few Hamiltonian paths. For example, you can go from A to B to C to D to E, and that's one example. So the argument I gave shows that it has no Hamiltonian circuit. And so if you go back and listen to that argument, or just look at the picture here, you can see that this graph does not have a Hamiltonian circuit, but it does have paths. Right. Okay, and so, so we're going to talk in more detail about this algorithm that was introduced last time. So this is an algorithm due to the, I think, Norwegian mathematician, I believe the way you pronounce this name is supposed to be Dijkstra. And so we ran through this algorithm without really talking about it very precisely, and sort of an informal example where we looked at a simple graph and we found the shortest path from one point to another using what would probably appear to be a kind of a convoluted process, because for that particular graph, you could just eyeball it and see what the shortest path is. Although, of course, in a lot of interesting problems, there are going to be a lot of vertices, so you're not going to be able to just find the solution by guessing and checking. And so this is why this algorithm needs to be developed. And so we're going to talk about it now in more detail. And so what I would recommend is trying to keep a simple example in mind as I go through this. For example, maybe take out a piece of paper and copy the graph that I'm about to draw down, and try to, as I go through the steps, run through these steps by hand for this particular graph, right? And this is always good advice when you're learning a new algorithm, right? You don't want the example to be too simple. Like, I don't just want a graph with 3 vertices, but maybe like 5 or 6, right? So let's try this one. Right, and so there's going to be a particular weighted graph. Right, so this is my graph G. Right, and I want to, so the general problem is finding the shortest path when taking the weights into account from A to Z. Right, and so this is the problem that Dijkstra's algorithm solves. And so what's the main idea of the algorithm, which is something we mentioned last time? Well, in order to solve this problem, you need to find, well, if you're going to find the shortest path from A to Z, how are you going to do that? Well, at some point along the way, you would have had to find the shortest path from A to some vertex which is connected to Z. Right, so in particular, if you're going to solve this problem in general, you need to find the shortest path from, sorry, one second, from A to all vertices which are connected to Z. And then among those paths, find the one which is actually the smallest, right? So if I'm going to get from A to Z, right? So maybe this was like some vertex x1. That's one way to do it, right? So I don't know. So the dot 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 is some path you're traveling through the graph. But maybe there's some other vertex x2 which I also can eventually get to from A. And so you have to first determine, well, what is the shortest path from A to x1, and what is the shortest path from A to x2? And then with that information in mind, then see, is it faster to get from x2 to Z, or from x1 to Z? And then you're going to pick the corresponding path, right? And so there's a sense in which in order to solve this problem, you actually have to solve it several times, right? You're not just trying to find the shortest path from A to Z. You're trying to find the shortest path from A to other vertices which are connected to Z, and then comparing those. And in order to solve that problem, you're going to have to solve even smaller versions of the same problem, right? So there are sort of a lot of nested copies of this problem built into it. And like at each level, it gets a little bit simpler. And so the algorithm is designed to take this structure into account. And you work in the simplest case, and then you slowly build your way up from A until you find a path to Z, exploiting these ideas. Right, and so let's go through what the algorithm does. So during this lecture, I'm just going to describe what the algorithm is in general, and maybe say a little bit about indication about why it works. And then what I'll do is type up an actual proof that it works and send it to you in a PDF, because if I were to go through the proof in the lecture, it would take more than an hour probably. And I already want this lecture to be a little short since the previous one went over time. Great. Right, so but let's go through the basic steps though. Right, and so there's going to be two main objects. So we're going to have a set S, which keeps tracks of vertices. Of vertices which we know information about the shortest path, right? So keeping track of vertices for which we know the shortest path from A. So it's not going to be immediately obvious from the algorithm that the set S that I'm going to talk about actually accomplishes this. It's something you have to prove, which we will prove later on. And so there's also going to be a collection of labels for the vertices, which keep track of the best known or the shortest known path from A to the vertices. And so these labels will change as the algorithm progresses, and then as we get a better understanding about the fastest way to get from A to another vertex. Right, from A to whatever vertex. And in particular, we're actually studying, this algorithm takes the whole graph into account, which is what you need to do in order to solve this problem. And as I mentioned before, along the way, it actually solves similar subproblems. For example, if you look at the graph above, when you run this algorithm, you're also going to find the length of the shortest path from A to E, and also the length of the shortest path from A to C, and so on, right? Right, so it's broken up into several steps. And so step 0 is when you initialize. And so we're going to just set S0, right? So it's not going to actually just be the set S. There'll be the set S will grow. It'll have some indices. So S0 will begin just by being the empty set. And then we're going to define our labels. Well, we're going to label all vertices V in the vertex set. Well, I'm going to let the labels are also going to change with each step. So I'm going to index them according to the step. So here we're in step 0, so I'll have L0. I'm going to let LV equal infinity if V is not equal to A. And then L0 of A will be 0. And this is just a technical thing. You'll see why I'm doing this in a second. Right, so step 0 just initializes. It doesn't really do much interesting. So what is step 1? Well, now I'm going to update my set S. So I'm going to join A to my set S0, right? And so in particular, S1 is just going to be the singleton set that contains A. And what we did was we added the vertex with smallest label from the previous step. Right, in the previous step, every vertex except A had label infinity, so A had the smallest label. And this is how the algorithm will work in future steps. Right. And so this is the first part where we update the set S. And then the second part of step 1, well, we're going to update the labels. Right. And so we're going to define new labels where I'll set L1V, where V is a vertex, to be the length of the shortest path from A to V, which only contains vertices which are in S1 and V. Right. And so, right, so what do I mean? So we have this point A, and then we maybe have some vertex V. So if there's a path, well, a path that only contains vertices in S1 means that it only contains A, right? And so in particular, it has to just be an edge connecting A to V. If there is no path, we just keep the label equal to infinity. Right, so step one is actually simpler. So what I'm going to do is I'm just going to look at all of the vertices which are connected to A by an edge, right? And so there's going to be some weight on the edge, and the label of the vertex L1 is going to be that number. It's the whatever the weight is, right? So remember, when we're talking about weight, or when we're talking about length, it's actually taking weights into account. And if a vertex is not connected to A, we keep the label infinite. And so the reason I wrote it out in this more complicated way is because now it will match up with what we do in future steps, where it becomes a little bit more complicated. Okay, and so that's step one. And now step two, what we're going to do is something similar, right? And so I'm going to update my set S. So in the first part of step two, I'm going to update S1 to S2. And so how am I going to do this? Well, I'm going to take S1 and I'm going to join a particular vertex U. And U is going to be the vertex which had the smallest label from the previous step. Right? So U is vertex with L1 of U smallest from the previous step. In particular, it's not going to be infinite unless the graph only has like one vertex, or it's not going to be infinite, right? And so among the list of those with finite label, you pick the one with the smallest. If there are two vertices which have the same label and they're both the smallest, you just pick one arbitrarily. And so one thing that's worth pointing out is that this label is the length of the shortest path from A to U. And again, when I say length, I really mean weighted length, but it's the length of the shortest path from A to U. And this is just by construction, because, well, if U has finite label, that means U is connected to A by just one edge. And so the length of the shortest path is just the weight of that edge, right? But what's going to turn out, which is something we'll prove later, is that these labels, as soon as you add a vertex to the set S, the label actually tells you the length of the shortest path from A to that vertex, which is why this algorithm works. Right, and so that's how you update the set S, and then what you want to do is update the labels. And so you're going to update the labels in the following way. Well, instead of L1, now I'll have labels L2. And so this is going to be the length, again, the weighted length of the shortest path from A to V. But the path is only allowed to include vertices in S2 and V. Right, so maybe my point A is over here, and maybe this is the point U that I added to create S2. Well, if V is connected to U, then L2 of V, right, I'm allowed to consider the path from A to U to V. And also if V was maybe let me do V prime, I would also be able to update the label of this vertex V prime because it's directly connected to A, right? So if a vertex, I'm only updating the vertices that I can reach on paths that are allowed to contain A and U, which are the two elements of the set S2, and then also that vertex. right? So these are two examples of vertices which I could update, for which I could update the labels according to the lengths of these paths. And so if there's no such path, we keep the label equal to infinity. And that very well may be the case that there is no path, right? For example, what if I have like a W over here? Then the label of W would be infinity because I can only reach W by going A to U and then to V and then W, but V was not in my set S2, so that would stay infinite. One thing that's worth pointing out is that, let me put this in. Right. So suppose we're in the first situation, or where I have A to U then B. Right. So suppose I have this connection. Well, if we're actually calculating the length of this path, notice that the path from A to U we already know. So this is already stored in the algorithm, right? Because the length of the path from A to U is just the label of U. Right? And so if we write this as an algorithm, well, in order to make this efficient, we really only have to just look up that value, which is already stored. So we can do that in one step. We don't have to consider what's happened in the graph before that. And then we just calculate the weight between U and V, right? Right. So we only need to add the weight W between U and V to the previous information we had about the label of U. I noticed the label of U is kept the same, right? Because the length of the shortest path from A to U in S2 is just the length of the path that we already knew, right? And so the key point which makes this algorithm efficient is that we already knew this information, and we just have to add one number to this bit of information to update the label for V. We don't have to look through the whole graph to get to V to update the label. And so maybe at step 2, it's not very clear why this is useful, but if you do this in a particular example and you get to like step 4 or 5, you'll see that keeping track of these labels in the way we're doing here allows you to update them very quickly without having to like go back a few steps in the graph. And so this will lead to the algorithm being relatively fast. Right. Okay, and so that's an indication of how the first few steps work. Now let me go to the general steps. So what do we do at step K? Right, where K is just any number. Right, and so we follow the same process. So we're going to update my set S. And so Sk is going to be formed from Sk minus 1 by adding a vertex U, where U is a vertex which is not in Sk minus 1, right? We want to add new information. With smallest label. So with the label Lk minus 1 U from the previous step as smallest. And then we update the labels, right? So once we update the set S, K minus 1 to Sk, we update the labels. And so we let Lk of V be the length of shortest path from A to V. But again, we're only allowed to consider paths which are in Sk. Right, which only contain vertices in Sk and also V. Right, and so if there is no such path, again, we keep the label infinite. I mean, eventually all the vertices will have labels because there's only a finite number of vertices, but if there still happens that there's no path, then we keep the label infinite. Right, and so this is how step K works in general. I want to point out an important observation. Right, so let's suppose we have a vertex where the label is finite, which means there actually was a path from A to V in SK. Right, so there's two possibilities in this case. Right, so the first possibility is that the shortest path from A to V in SK does not contain the vertex U, which was just added. So I don't mean the U from a previous step, I mean the U that was added at step K, at this step. Right, well then the shortest path from A to V is actually in SK minus 1, right? So in particular, we don't update the label at all, right? So the path is in SK minus 1. So the new label is just the same as the old label because I'm just going to use exactly the same path I did in the previous step, right? So LKV is LK minus 1V, and there's no change. Sorry, I want to make sure my V's don't look like U's. Oh, okay. Okay, and so that's the first possibility. The second possibility is that U is in the shortest path from A to V. Great, so either U is or it isn't. So the second possibility is the case where it is. Right, and so what does the picture look like? Well, I have my vertex A here, and then there's some path in the graph. I don't know exactly what it looks like, but eventually I'll hit U, and this is the shortest path in SK from A to U. And then I can get from U to V with some weight, which I'll call WUV is the weight connecting U and V. Well, I already know the length of the path from A to U. So this is just the label from step K minus 1 of U. And in particular, my computer doesn't have to calculate this. It's already stored. And so then I can find the label for V just by adding the W to this previously stored bit of information. And so in this case, let me change color just because it's getting cluttered. So in this case, LKV is equal to LK minus 1U, which is the length of getting from A to U, and then plus the weight from connecting U to V, right? Whatever the weight is on the edge that connects U to V, right? And so these are the two possibilities. So either I update L in this way, or in case 1, or in the manner in case 2. And so since I'm always choosing the label to be as small as possible, we obtain the following equation. So LK minus 1, or sorry, LK, the label at step K for V, is the minimum of the two previous cases. So it's either in the first case, just LK minus 1 of V, or it's LK minus 1 of U, where U is what was added, right? So SK is SK minus 1 union U, and then plus the weight from U to V, right? And in particular, well, these two things are functions of K minus 1, so these are already known, right? And so this is why the algorithm will be efficient, right? We update it based on already known stored information, and we only have to do a handful of calculations, right? Right, and so you can see from this that this problem, this equation illustrates the recursive structure of the problem, right? Because I'm updating my labels using information about labels from the previous step in a recursive manner, and so this is also an example of this dynamic programming principle. If you know anything about that, you don't have to for this class, of course. But if you have heard, as I mentioned before, if you have heard in a math or computer science class about dynamic programming, this algorithm is sort of like the go-to example for what dynamic programming is, right? Because I'm using smaller versions of the problem to solve bigger versions of the problem, right? And so if you ask certain people, this is sometimes referred to as the Bellman equation. for the problem after Bellman, who was a mathematician and computer scientist, who was one of the first people to develop these types of arguments. And so when we actually prove that this algorithm works, this equation is going to play an essential role in the argument. Okay, and so that's how step K works. Well, the algorithm's not going to go on infinitely, so what is the stopping criteria? When does it stop? Well, the algorithm stops at step M, and I'll tell you how you find M. Well, it stops exactly at the step M when Z is added to the set S. Right, so SM at the step when I find SM by adding Z, right, where the U that I add turns out to be Z, then the algorithm stops. And so the theorem, which is not at all obvious from what we've talked about so far, but the theorem is that this algorithm actually works, meaning that the label of Z at this step is the length of the shortest path. Right, so if the algorithm stops at step M, meaning that's when we just added Z to the set S, then the label of Z is the length of the shortest path from A to Z. And so these labels keep track of as you update the label, they get closer and closer to solving the problem. And when the algorithm finally stops, the label tells you the length of the shortest path from A to Z. Again, length of shortest weighted path. Right, so this is weighted. And in fact, so at least in the book, it's not stated like this, but if you do any example by hand and you run this algorithm by hand, you're always going to not just be able to find the length of the shortest path, but it will also tell you like what the shortest path is if you do all the steps, right? So this is a way of also finding the shortest path, not just finding the length of the shortest path. Okay, and so how does the proof work? So I'm going to send a handout or a file over email, which will have the proof written out in detail. You can also look in the book, although I think the proof in the book leaves out some important steps and maybe a little bit confusing without some extra elaboration, which I'll try to do. But the idea is the following. So you prove the following two things by induction. Right, so remember this algorithm has some kind of recursive structure, right? So you're using smaller versions of the problem to solve bigger versions of the problem, and so intuitively it makes sense that you would probably prove that it works using induction, which is what you do. And so you actually prove two different things by induction. So the first claim is that if I have a vertex in the distinguished set Sk at step K, right? So this is at step K. Then the label, the kth label of V, is the solution to the problem for V, not for Z. So this is the length of shortest path in G from A to V, right? And on the other hand, if you have a vertex which is not in the distinguished set Sk-1, say, then we'll show that the label of V, it's not necessarily the length of the shortest path in the graph, but it is the length of the shortest path in Sk, which are two distinct things, right? right? So containing only vertices in sk minus one. And so this is how the proof will work, and you'll see if you're interested in understanding the argument. You'll see how to prove these two things in the PDF I send you. Right. So why does this imply the theorem? Well, the theorem follows from case one. When k is equal to m, right? Since then z is in sm, right? And therefore the label of z is the length of the shortest path. Right, and so this is actually a kind of the structure of this proof is interesting, right? You don't prove it directly. You don't prove directly that this is that the label of z is the length of the shortest path. You prove a more general statement about basically every vertex in the graph, and this statement is broken up into two parts, both of which you prove by induction on k. And then all this extra information allows you to get just the information about z that you want. So it's sort of like you're using a lot of power tools to prove the theorem, although there's not really any other way to prove this, because you have to basically take into account the whole graph is the idea. All right, and so I just want to say a little bit more about weighted graphs at the beginning of the next lecture. I'll talk briefly about the traveling salesman problem, which is a famous problem in computer science. And then we'll start talking about some more geometric things, which are related to things called planar graphs. So we'll talk more about that on Friday.